Bismillahirrahmanirrahim. Assalamu alaikum students, welcome back. Welcome to this online lecture series on electronic devices and circuits. This is Owais, your course instructor. The weekly schedule for our online lectures for this course. So the references are cited here. The textbooks. And now the topic which we started in our previous lecture, rectifier circuits. So how is a full wave rectifier different from a half wave rectifier? Yeah, the name itself gives you an idea, as a full wave rectifier is a circuit that allows unidirectional current through the load during the entire input cycle, whereas for a half wave rectifier circuit you had it only during the positive half cycle. So the output waveform is also shown here, so you can relate the input waveform and the output waveform. How do we get this output waveform? We shall discuss this in the upcoming slides. But here you can see that you are getting output not only during the positive half cycle, but also during the negative half cycle as well of the input waveform. So the output can be seen as continuous, whereas we had breaks during the half wave rectifier as the half of the input cycle was not being rectified. Students, can you find out the relation between the two frequencies? What is the relation between this output frequency and the input frequency? So for that, let's use the same concept as we had for the half wave rectifier. Let's find out the time period. So roughly, this is the time period for the input, and this is the time period for the output. Okay, let me. Yeah, so if you see the time period for output waveform, for your output waveform is half that of the input waveform, which means the frequency will be double that of the input frequency. So output frequency will be double that of the input frequency. It will be twice that of your input frequency. But what about the average value? Any idea about average value? Okay, let's discuss that in the next slide. Yes, it's exactly the same way as the frequency. So for a half wave rectifier, if you remember, average value was Vp divided by pi. And for a full wave rectifier, since it's exactly the double of the half wave rectifier, the average value gets multiplied by 2. So, and it makes sense as well if you see the output waveform. So the average value can be simply written as 2 times that of the average value of the half wave rectifier. But you can also derivate this relation to find out this relation by simply considering this period and applying the same integral formula as we did when we were studying full half wave rectifier, and you will see that the relation is exactly the same as given here. So in this example, you have been asked to find out the average value of the full wave rectifier. You need to find out the peak value, and this peak value is given as 15 volts. And if you simply put it into this equation, you get your average value. Okay, now let me introduce the circuit for full wave rectifier. Both these circuits are nothing but the full wave rectifier and are 100% the same. You may be getting confused by the two different circuits. Actually, these are exactly the same, but there is some difference of the nomenclature. This circuit is from Thomas Floyd 9th edition, whereas the circuit in this lower part is actually from Sedra Smith 7th edition. Now you see here, this is a center tape rectifier. Sorry, the center tape transformer. And why do we call it a center tape transformer? Because the secondary winding is actually divided into two halves, into two windings. And these two halves are divided equally, which means that you have two tappings and a tapping at the center of the transformer. So essentially the winding is divided into two halves, which means the secondary voltage is also divided into two halves. So half of the voltage appears between across the center tape terminal and the positive half or one half of the winding, and similarly the other part of the center tape also gets the same voltage. So voltage gets distributed equally as well. You are using two diodes, diode D1 and D2, and a load resistor. Now the circuit shown here is exactly the same, except for the difference that we have used a single ground, and you know that electrically whether you use a single ground like this or you use two different grounds, these are exactly the same. So there is no difference as far as the working or the circuit of the circuit is concerned. Now, a slight difference is in the nomenclature. Here, the secondary voltage has been shown being divided into two parts as V secondary over 2 and V secondary over 2. So if you add these up together, you will get the overall secondary voltage, and that secondary voltage in this nomenclature is given by V secondary. Whereas in this circuit, the half voltage that appears across the half of the winding is given as Vs. So the difference, there is no difference between the two circuits. When you add up these two voltages together, you get total secondary voltage as 2Vs. Okay, so please remember that this voltage, total voltage across secondary and total voltage across this secondary is the same. It's just the difference of the nomenclature. So for instance, if the total secondary voltage is defined is given as 40, then you can say that V secondary over 2 is equal to 20. Okay, whereas for this circuit we will say that okay, yeah, Vs is equal to 20, and the total secondary voltage in this circuit will be given by 2Vs as equal to 40 volts. So let's continue with this circuit. Maybe it's more easier for you to understand how current flows actually into my load resistor. So as discussed in previous slide, the voltage has been divided into two parts, V secondary over 2 and V secondary over 2. It's exactly the same. Okay. So using these two diodes, we shall see how we are getting an uninterrupted output voltage. So let's first discuss the positive half cycle. Now during the positive half cycle, uh, the polarity can simply be given using this. So positive here and minus here. Same relation can be seen on the secondary as well. So a positive here and a negative here, positive and negative. So now we need to see which of the two diodes are conducting, or are both of these conducting. If you have a look at this diode D2, can you figure out whether this will be forward biased or reverse biased? And if you pay attention, you will realize that this diode is actually reverse biased. Why? Because the voltage at its anode is more negative as compared to its cathode. Therefore, essentially this diode is not conducting and it's reverse biased. So the only diode that is conducting is now is D1. So now we need to find out how current flows through this diode into my load resistor. And if you see, current is flowing from ground and then going through diode D1 and into my load resistor and back into ground. So the loop is being completed and current flow can be seen. And if you see that, you will get some output voltage. We shall find out the relation for this output voltage. But at this moment, you need to realize which of the diode is conducting and why is it conducting. Okay, now let's discuss the negative half cycle. So during the negative half cycle, again, the polarity at the input side is given the same way. So we say this is a minus here and a plus here. Same has been shown on the secondary side as well, minus plus. And now with this polarity, it is quite easy to understand that which of the diode will be conducting. Yes, you guessed it correctly, diode D2 will be conducting, whereas diode D1 will be reverse biased. Again, you see how current is flowing. An important point to note here is that current again here flows into diode D2 and it goes into my load resistance exactly the same way. So from into plus then into minus ground. Okay, so current is flowing in the same direction into my load, whether it's the positive half cycle or the negative half cycle. The current flow into the load is exactly the same. That is why you get the same output voltage during the positive half cycle and during the negative half cycle as well. Okay, now let's find out what is the voltage across my output voltage or my load. Okay, what is my output voltage we need to identify. So on this slide you can see both the positive half cycle and negative cycle. हमने देखा कि दोनों केसेस में मेरे पास सेम आउटपुट आ रहा है. So positive half cycle भी आ रही है और negative भी आ रही है मेरे पास. Now we need to find out what is the value or what is the value of the voltage appearing across the load resistance RL. तो उसके लिए if you focus here, you will find out that this voltage is exactly found out in the same way. It's find out in the same way as for a half wave rectifier. So हमें ये मालूम करना है कि what is the voltage that is appearing across this half winding, and then we will be able to apply a KVL. So KVL हम किस तरीके से लगा रहे होंगे आपको मालूम है. KVL कैसे होंगे? If this is V secondary over 2, so we write it down as minus V secondary over 2, and if this diode has a drop of 0.7, so minus V secondary over 2 plus 0.7 and plus V naught. Okay, so V naught will be then equal to V secondary over 2 minus 0.7. So whether we discuss this case or we discuss this case, we will get the same relation. Again, if you apply KVL this across this loop, you will see that this is minus V secondary over 2 plus 0.7 plus V naught equal to 0. And this you will again get the same relation. So V out will be given as V secondary over 2 minus 0.7. Now this V secondary over 2 is please make sure that your concepts are pretty clear, that this V secondary over 2 is simply the voltage that appears across the half of the winding. So whatever the value of this is simply V secondary over 2. Okay, so now let's see how the output waveform actually appears. Now this waveform is exactly uh, obtained in the same way as for the half wave rectifier. The only difference is कि यहाँ पे अब आपको negative input cycle के दौरान भी you can see the waveform, the output waveform. Again ये जो आपके पास यहाँ पे difference आ रहा है between the input voltage and output voltage, this gap is of VD, and this VD is generally 0.7 for a silicon diode. And again यहाँ पे भी जो आपको delay नजर आ रहा है is nothing but the same concept as we discussed in the full wave rectifier. So अगर यहाँ पे आपको कोई query हो रही है, please go through the previous lecture and you will be able to understand that why do we have this sort of a delay. So you see that during the positive cycle it's conducting and during the negative cycle it is conducting, though we have a period or a region in which the diode is not conducting. Time to discuss the voltage transfer characteristic curve. I think this should make sense to you because this is the same concept as that of the half wave rectifier. Half wave rectifier में क्या हो रहा था हमारे पास initially diode was not conducting क्योंकि these are practical diode. अगर मैं चूंकि ये दोनों diode का drop हमने assume किए same VD, but अगर मैं कहूँ कि ये VD1 है और ये VD2 है, तो आपकी आसानी के लिए मैं यहाँ पे इसको हम कह सकते हैं कि now this voltage is VD1 and this is VD2. यहाँ देख सकते हैं जैसे ही हमारे पास वोल्टेज इनपुट वोल्टेज Vs, अगेन अगर आप पिछले सर्किट में देखें तो वहां V secondary over 2 लिखा होता, यहाँ पे हमने Vs लिखा हुआ. It doesn't matter at all. Make sure your concepts are pretty clear. So जैसे ये वोल्टेज मेरे पास सेकेंडरी वोल्टेज, जैसे ही मेरे पास सेकेंडरी वोल्टेज से मुराद जो हाफ में डिवाइड हुआ है, दिस वोल्टेज जैसे ही मेरे पास 0.7 से exceed करेगा, the diode D1 will start conducting, and we will see that the output will be exactly same as that of the, it will be following the input exactly the same way. That's why I'm getting slope यहाँ पे क्या है 1. अच्छा जी, अगर हम नेगेटिव में बात करें, हाफ वेव में कंप्लीट साइकिल के दौरान पूरी नेगेटिव इनपुट के दौरान आपके पास आउटपुट वाज जीरो, बट हियर दिस इज नॉट द केस. यहाँ पे क्या हो रहा है आपके पास, ड्यूरिंग द नेगेटिव हाफ साइकिल दिस डायोड स्टार्ट्स कंडक्टिंग आफ्टर दिस ड्रॉप ऑफ 0.7, और आपके पास क्या होता है, आउटपुट वोल्टेज की क्या वैल्यू आती है, आउटपुट वोल्टेज आपके पास पॉजिटिव आता है या नेगेटिव आता है, द आउटपुट वोल्टेज अपीयर्स पॉजिटिव. दैट्स व्हाई हमने इसको नेगेटिव में दिखाने की बजाय कि हम यहाँ नेगेटिव में दिखा रहे होते, हमने दिखाया कि आउटपुट वोल्टेज इज अगेन इट इंक्रीजेस. ठीक है, सो आउटपुट वोल्टेज इंक्रीजेस in the relation between the applied secondary half voltage and output is pretty the same way as for the positive half cycle. माइनस क्यों लिखा हुआ है जनाब, यहाँ पे माइनस हमने इसलिए लिखा हुआ है क्योंकि the voltage input voltage Vs is negative in this region, whereas the output voltage is positive. Therefore, the slope is given as -1. So this is called the voltage transfer characteristic curve. Whenever you are asked to draw the voltage transfer characteristic curve, you need to know कि हम y एक्सिस के ऊपर V0 को रिप्रेजेंट कर रहे होते हैं और x एक्सिस के ऊपर अपने इनपुट वोल्टेज को. Okay, students, let's find out the peak inverse voltage for this half wave rectifier. Sorry, the full wave rectifier, center tape full wave rectifier. And for finding out the value of the peak inverse voltage, we have to consider the diode which is reverse biased. So either you consider D1 or D2. So if we are considering D2, then we are actually referring to the positive half cycle, because during the positive half cycle diode D1 is conducting and diode D2 is reverse biased. So we find out what is the value that is appearing across this diode D2, and that will be given as my peak inverse voltage. This is how do we find out peak inverse voltage? It's this and this. So peak inverse voltage is given by, so this voltage minus this voltage. Okay, so what is the value of voltage at this point, and what is the value of voltage at this point? At this point it's pretty clear that the value is nothing but minus Vs. Okay, why? Because why minus Vs? Because you have a negative terminal here, so you get minus Vs. What will be the value at this point? If you pay attention, you will see this point is connected to the output voltage at this point, so this voltage will be nothing but my output voltage. Okay, so then this is my V naught, and this is minus Vs. Minus Vs. So peak inverse voltage will be given by V naught minus Vs. And this V naught is nothing but Vs minus Vd. And if you put it into this relation, which is V naught plus Vs, you will simply get this value of 2Vs minus Vd. This is the peak inverse voltage of a full wave center tape rectifier. Why do we have used this capital Vs? Because this capital shows the peak value. When we write down capital Vs, this means the peak value of my input voltage. So we have to consider the peak value in order to find out the peak inverse voltage. If you do not put the capital value of Vs, or if you do not write it down as capital Vs, then this means that your interpretation is not clear. Okay. So with this, we are done with our discussion on full wave center tape rectifier. Now this is just an example or a homework for you students. What you need to do is you need to come up in our next class, the interactive or the in the next interactive session. Please solve this circuit, find out the value of V out, what is the value of V out, and what is the peak inverse voltage. I want all of you to solve this circuit before coming into the interactive session. And if you face some confusion, if you find some difficulty, don't worry about it. Just give your best try. We shall discuss it in the interactive session. Okay, now it's time to discuss full wave bridge rectifier. This is another type of full wave rectifier. and this is called bridge rectifier because of its configuration, and it's pretty similar to Wheatstone bridge, which you must have studied in your physics course. And now let's discuss how this circuit works and how do we get our output voltage. If you pay attention here, this is the same AC input voltage which is being applied on the primary of the transformer. And here the transformer, this is not a center tape transformer. So the entire voltage appears across the secondary of the transformer. And then we have actually four diodes connected in a certain way, and the voltage across the output will be taken this way. So I will soon show you another configuration of this circuit which is exactly the same circuit, but it's just shown in another way. So this is a circuit which I was referring to in my previous slide. This circuit is exactly the same as the previous. Again, what you see is the ground there. Two grounds have been shown, and these two grounds are exactly the same. So what you can do is you can simply connect this resistance RL at this point directly instead of showing it separately. This has been shown just for convenience so that we can simply analyze our circuit more easily. Now this is a bridge rectifier. It consists of four diodes as discussed previously. So it's up to you how you name these diodes, D1, D2 this way or D3, D4, it doesn't matter. You need to identify that which diodes will be conducting during the positive half cycle and which diodes will be conducting during the negative half cycle. So here we are discussing and we are considering only the positive half cycle. So the polarity has been shown here, plus minus, just the same way, exactly the same way when we were discussing the center tape rectifier. So now let's see which of the diodes are conducting and which diodes are not conducting. If you pay attention, then you will see that diode D3 is reverse biased. Why is it reverse biased? Because you see at the anode the voltage is less or zero as compared to the voltage at this point. Thus diode D3 will be reverse biased. And if you see diode D4, you will realize that diode D4 is also reverse bias. Why is it reverse bias? You see the negative come appearing here. So this means that the anode is actually at lower potential than that of the cathode. Therefore, the diode D4 is also reverse biased. Okay, let me rub this out. Now we have identified the diode D4 and diode 3 are reverse biased. And if you pay attention, you will realize that diode D1 and diode D2 both are forward biased. You see, if you pay attention, diode D2, this ground is at a higher potential as compared to the negative voltage on this side or on the cathode of diode D2. So thus diode D2 is also conducting, and in the same fashion diode D1 is also conducting because the voltage at the anode is a higher potential as compared to the voltage at the cathode. So diode D1 and diode D2 are conducting during the positive half cycle. So let's examine how current will be flowing. So we can do it in any fashion, but if we start from this point, from the positive, we see the current flows into diode D1 and then into my load resistance RL. The current is flowing this way, and from ground, since the two grounds are exactly the same, it again flows back into diode D2 and this loop gets completed. The important point to notice here is that in this loop we actually encounter two diodes, diode D1 and diode D2. So the output voltage, and at the output we will have the drop of two diodes, diode D1 and diode D2. So if you can figure out it, it's pretty easy to understand what will be the value of the output voltage. This output voltage will be nothing but the secondary voltage minus the two drops of the diode. How do I say this? Is by simply applying KVL. If you apply KVL across this loop does not finish here at this point. So from ground it again current flows into diode D2 back into the secondary of the transformer. This is how the loop is being completed. So you get the voltage drop of two diodes. So output voltage is V secondary minus 2 times the drop across the voltage, across the diode. So now let's consider the negative half cycle. So exactly in the similar way we consider the negative half cycle, the polarities are shown here, minus plus and minus plus on this side as well. Again, using the same analysis method we had done previously for the positive half cycle, you will be able to identify that in this case diode D1 and D2 will not be conducting. Okay, so these are not conducting, and the diodes which are conducting are diode D3 and diode D4. So the loop gets completed the same way. Okay, so if I flow in this direction, I go into diode, I current flows into diode D4, into the load, and back from ground into diode D3 and into the negative terminal or the secondary. So the KVL, if you apply the KVL, you will again realize that there are two diode drops, drop of diode D3 and drop of diode D4. So again, the output voltage is nothing but V secondary minus 2 times the voltage drop across the diode. Again, it's important to focus that the current flowing into the output, which is the load resistor RL, it's exactly in the same way as during the positive half cycle. So the polarity of the output voltage remains the same. In this, you get continuous half cycles on your output at your output. So as discussed previously, this output voltage is Vs minus 2Vd. And why is this drop of 2Vd? It's very obvious. We discussed previously. We had two diodes. We encountered two diodes while we applying the KVL. So this is given by V naught is Vs minus 2Vd. If you are interested in finding out the peak value of the output voltage, what you have to do is that you need to replace this Vs. You need to replace this Vs by capital Vs. So then you will get the peak value at the output. Okay. So as far as the peak inverse voltage is considered, I have told you how to find out this peak inverse voltage. What I want from you students is that please identify how are we getting this relation. So that you get an insight into the circuit and you get into the practice of finding out the peak inverse voltage instead of just simply memorizing the values. So please solve this for our circuit for the bridge rectifier. This is your home task and we shall discuss it if you have any confusion during our interactive session. So this is again the same output waveform between the relation between output and input. It's exactly the same as for center tape rectifier, but the only difference in this case is now of 2 VD. So the voltage drop will be 2 VD. The difference between the input and output will not be 0.7 or VD. This will be actually equal to 2 times VD or simply 1.4 volts. In this delay will exactly be determined the same way as for center tape rectifier, but with the difference that now the voltage to be considered when the voltage will start appearing, it will be actually 2 times VD instead of single VD. Okay students, now we have an example. This is for a full wave bridge rectifier. We have to find out the value of peak output voltage for the given circuit, and we also have to find out the value of the peak inverse voltage. And the model is actually a practical model, which means that the voltage drop across each of this diode is 0.7 volts. So अगर आपको ये voltage मालूम है और बाकी पैरामीटर्स मालूम है, तो बड़ा आसान होगा आपको इसको सॉल्व करने के लिए. So let's see हमें और क्या given है. We have been told that the input voltage is 120 volt and the secondary voltage is 12 volt RMS. Please pay attention that the voltage which has been specified here is RMS voltage. RMS means root mean square value. Even अगर आपको RMS value नहीं given होती और यहाँ पे simply 120 volt लिखा हुआ होता, this should have been enough for you, because whenever we are talking about AC waveforms, the voltage is always RMS अगर आपको स्पेसिफाई नहीं किया गया है। अगर आपको बता दिया गया कि इस पीक वोल्टेज, then you can take it as peak voltage. But if nothing is mentioned, always assume it to be the RMS value. अच्छा जी, सेकेंडरी के ऊपर जो RMS वैल्यू है दिस इज 12 वोल्ट्स और प्राइमरी पे 120 है, तो टर्न्स रेशियो कितना हो गया जी? इज सिंपली 12 डिवाइडेड बाय 120 एंड इक्वल टू 0.1. Okay, so 1:10, or 10:1. So 10 is on the primary side and 1 on the secondary side, a step down transformer. So आप सिंपली इसे रिलेशंस के अंदर जब पुट करेंगे, जो हमने पीछे डिस्कस किए हैं, बहुत आसानी से आप पीक इनवर्स वोल्टेज भी निकाल लेंगे और आप पीक आउटपुट वोल्टेज भी निकाल लेंगे। थोड़ा सा एक छोटा सा ट्विस्ट है यहाँ पे। वो ट्विस्ट क्या है कि हमारे पास जो वोल्टेज है वो आरएमएस वोल्टेज है, और हमें क्या करना होगा, हमें इस आरएमएस से हमें वी हैव टू फाइंड आउट द रिलेशन बिटवीन the RMS voltage and the peak voltage. What is the relation between the RMS and peak? For that, what you need to do is you have to go through the slides which I shall be uploading on LMS, and from after studying and going through those slides, आप बड़ी आसानी से ये relation जान सकेंगे between RMS and the peak value. बट आपके लिए एक असाइनमेंट है, एक होम टास्क है कि यू नीड टू फाइंड आउट और यू नीड टू बी एबल टू डिराइव द रिलेशन फॉर रूट मीन स्क्वायर वैल्यू। ठीक है, सो यू नीड टू फाइंड आउट व्हाट इज द रिलेशन फॉर रूट मीन स्क्वायर वैल्यू ऑफ एन एसी वेवफॉर्म। ठीक है जी स्टूडेंट्स, आज आई थिंक इतने इस लेक्चर के लिए इतना काफ़ी है। दैट्स इनफ फॉर टुडे। Please go through the lecture, and if you find any difficulty, any confusion, write down me an email, or you can ask questions during the interactive session. Thank you so much, students. That's it for today. Inshallah, I shall see you in the next online session. Assalamu alaikum.